Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 5, 6, and 7 in your Unit 3 homework. So let's talk about what we're looking at here. In this picture, there's a pair of parallel plates, right? One here and one here. And these plates are charged, as you can see in the photo. And what that means is now we're going to have an electric field between the plates. Right, in this region where this particle is apparently moving. So ask yourself, what is the electric field direction? And then calculate a magnitude. Now, one of the mistakes I see people make with the electric field magnitudes is they want to jump to this, like the electric field, kq over r squared. This equation is for finding the electric field due to a point charge. These plates are not point charges, so it does not apply. Now, we know the potential difference, that's given, and a distance. That's where you're going to get the field strength from, right there. Now, once you know the field strength, now what we're going to do is, and I already put a picture here, draw a free body diagram of this object. So come over here maybe and draw a picture and put the Coulomb force in, the force created by the electric field. Now, reading further into the problem, we want this thing to move through here at constant velocity. In order for an object's velocity to be constant, right, that tells you something about the net force on the object. You get to put a force on there. You're going to put a magnetic force on there. So in your free body, put a magnetic force in such a way that the net force is 0. Keep in mind that the magnetic force, right, is given by QVB sine theta. And although I may not have mentioned it, I probably should go back and rewrite this, but I'm sure I meant to assume that the magnetic field makes a right angle to the velocity vector. So basically, this is supposed to be 1 in this problem. I don't think it's worded as such, but that was what I had intended. And that should allow you to write a force equation. Remember, the net force needs to be 0, and you should be able to find the magnetic field strength. Now, once you find the magnetic field strength, you also need to determine a direction, right? Right here, be sure to include the direction. So you have to look at the velocity vector, look at the force direction in your free body, and use your right hand to decide on the magnetic field direction that will give you the appropriate force. That's about all I can say without giving it up. So hopefully that gets you enough to get this problem moving on. Let's chat about number 6. Okay, so a proton starts from rest. There it is, right there. That's what we're talking about. And it's accelerated by a 500 Newton per Coulomb field over this region right here. Let's see, part A, use principles of energy to find the speed of the proton when it enters this region right here where there's a magnetic field. So write out the work energy theorem, PE1 plus KE1 plus work equals PE2 plus KE2. Now, how you take the electric field into account is up to you. All right, method number 1, you could use a work term. Calculate the force on this particle, right, due to that electric field, times this distance right there. That's going to be a work term. And then the speed will fall out of the kinetic energy term, you know, because you're going to have a 1/2 mv squared on the right-hand side. Now, that's one way to take the electric field into account. Here's another way. If we were to draw the equipotentials, I'm going to draw them in green. Remember, equipotentials always make a right angle to the field. So there's an equipotential, and there's another one over here, right before it enters the magnetic field, if you will. And let's call this one like potential 1 and this one potential 2. Now remember, potentials, you can define a datum. So if you think about like gravity, you know, what would be a logical place to put a datum? I personally would call this one a potential of 0. So if you do that, your PE2 would be 0. Your PE1 can be written charge times potential 1. So then it's like, all right, what do we do about this? Well, remember, potential difference is field strength times distance. And here's a field strength given and a distance. So that should be enough to get you through number 6 here. And I wrote an answer down. I got it about 69,000 meters per second when I worked it out. Hopefully I did it right, but again, I just kind of did it in my head with, using a calculator. Hopefully it worked out. Okay, now, part B. The proton then enters this region where there's a magnetic field. So let's say here's my proton. I'll put it right there. At the instant shown, going 69 meters per second to the right. Right? And there is a 20 millitesla, sorry that's hard to read, but that means 20 times 10 to the minus third teslas minus k direction. So that's going to allow you to draw a free body, but here's the object here, and that's going to put a magnetic force on that particle. Decide on the direction. Keep in mind the velocity vector is this way in the picture, and the magnetic field is in the minus k direction. So the magnetic force is QV cross B. That should allow you to put a force vector in this free body right here. However, I didn't put very much room there for that force. That'll give you an idea of the force direction. And let's see, what else do we got going on here? Part C, what radius of path would this proton undergo? So remember the magnetic force, when you calculate it, right, it's QV cross B. And the magnetic force always makes a right angle to both of these, the V and the B. When your force is at a right angle to the V, the proton won't speed up or slow down, but it will change in direction. That's going to force a circular path. Right? And when you have particles moving along a circular path, there's a very specific type of acceleration that's present here. Right? And a little reminder here. That means centripetal acceleration is present or important, and centripetal accelerations have a magnitude of v squared over r, and they're always directed towards the center of curvature. So that should be enough to allow you to write a Newton's second law equation for C. I got 3.6 centimeters when I worked it out. See what you get. Okay, number 7. So let's see. The rectangle shown carries a 20 amp current. So this is an example of what we call current loops. Now, the voltage creating that current, not important for the discussion here. So what you're looking at is this conducting material that carries a current, 20 amps, in the direction shown. Let's see, find the magnetic force on each branch. So what that's referring to, the branches are like, here's a branch, here's a branch, here's a branch, etc. Now, I gave the answer, this arrow means, right here, this means this branch right there. I gave you one of the answers. I'll let you get the rest of them. And when you calculate a magnetic force on a wire, it's IL cross B. So when we look at this branch right there, I is a given value, L is a given number, B is a given number. These are all given in the problem. And when you calculate a value, don't forget the ILB sine theta, where again, the theta is between the I and the B. Now you got to get used to thinking of 3 dimensions. In this picture right here, that current is pointing in the minus Z direction. So if we were to attach a unit vector, it'd be minus K. The magnetic field given right here is in the plus I. So you're going to ask yourself, what is the angle then between the I and the B? Right? And hopefully that's obvious. Now don't forget to do a direction. So remember the magnetic force, IL cross B. So your fingers go parallel to this vector, so they go this way. Rotate till you can sweep towards the magnetic field, which is in the plus I direction. That will give you the magnetic force direction. This is what I got right there. So confirm when you work it out, and don't forget to do the other 3 branches. So hopefully this set of videos will help get you through problems 5, 6, and 7. I hope you are enjoying them. Have a great day.